This
all is
conference will
necessary to
now
be
be
understood
recorded.
in the I2C communication protocol. We understood that, and we took an example also where we have to read the number of seconds from the RTC, and we have to display it on the CLCD of your board. Let me open that example, and we will try implementing the same in today's class. So we will implement whatever we have noted down the steps one after the other with independent functions in today's class. Now let me quickly go through the I2C communication protocol. We will quickly brush up the thing. So I2C is a synchronous communication protocol which helps us half duplexity to be achieved, and it's a multi-master multi-slave communication protocol. Then we saw the bus features where it's a two-line interfaced bus. It has a clock line, it has a data line. The devices in the network are software addressable. It's multi-master, so we also have collision detection. And serial data transmission happens, and all the devices in the network generally are 8-bit oriented. So they are bidirectional with 4 different modes. And we have on-chip filtering also. Now coming to the I2C's example, we saw multiple microcontrollers and multiple slaves being in the same network. We tried establishing the communication between one microcontroller and an ADC. So every line, whether it is a data line or a clock line, will have two wired interfacing. We are going to have wired and concept seen. Half of the part we achieve with the wiring concept, the other half with the AND. Then we have different conditions and data validity. I2C is a level triggered protocol. So at the low level of the clock pulse, data gets transmitted, and at the high level of the clock pulse, data gets received. So then also we saw that if the clock line is high and you see a change of the data in the data line, it must have been representing some condition, either the start condition or the stop condition. Then we saw how data gets transmitted on the SDA line, how clock pulse gets generated on the clock line. Then we have clock stretching, which happens when two microcontrollers are communicating with each other. One microcontroller is acting as a master, another microcontroller is acting as a slave. Then we saw clock synchronization, which happens when two masters start generating the clock pulse. So it is always the clock pulse depends on how the clock signal is being generated by individual masters. So there are chances where both the masters are going to generate the clock pulse at the same time of the same frequency. But there are chances where one of a master may have higher frequency, one may have a lower frequency. So we saw how synchronization between the two clock pulses happens. And we saw data arbitration, which is used to make a decision of whether which particular microcontroller is going to win the bus if both the microcontroller starts communicating their data at the same time. So we saw the complete data transfer and different bus speeds. Any doubts in this? Any doubts in the theoretical part? Okay. Now let us proceed with the programming part. So whatever we have done here, we are going to do the same. So whatever example we have taken here, we are going to do the same. So here the master is the PIC16F877A microcontroller and the slave is the RTC. Now we already have a driver code. Whatever we have tried achieving here, we already have a driver code for it. So we are going to look at it. So our microcontroller should go to the RTC whenever it has to read the number of seconds. So here communication is happening between two chips of the same board. Now if you look at the Pixim Lab board, let me identify where is RTC and where is the microcontroller. Okay, here it is. So this one is the microcontroller. Let me change the color. Okay. So this one is the microcontroller, the PIC16F877A, and this one is the RTC. So communication is happening between these two chips. So two chips of the same board. So it's an intra-board communication protocol. And we are going to establish this communication with the help of I2C. Okay. Now the problem with this is, whatever program I'm going to execute, where am I executing that program? Whatever program I'm going to write, where am I going to get that program executed? Come on, where will I execute the program which I'm going to write? So it is on my microcontroller, the PIC16F877A microcontroller. Now, you being in your microcontroller should program the RTC as well. So if you want to write, you have to go to the RTC. If you want to read, you have to go to the RTC. So being in your microcontroller, you are supposed to initialize two things. One, you have to initialize the I2C block of your own microcontroller, which supports I2C communication protocol. So first you have to do the initialization of the I2C block, which is available on your microcontroller, which helps you execute the I2C communication protocol. So that is the first thing. Being in your microcontroller, you also have to do the initialization of the RTC. So whatever basic initialization is required for the RTC, so you have to do it being in your microcontroller itself. Now, this is going to be a lengthy process. It's not like a very simple code. In fact, the code is very long because you have to do the initialization of the I2C block, because you have to do the initialization of the RTC block, then establish the communication between the two and follow all of these steps. It is going to take time. It is a lengthier code. So please have patience. It's a bit lengthier code as I'm saying. So you have to be patient and you have to understand everything we are discussing here, and you can let me know if you are getting any doubts in between. Now let us go with the programming part. Sorry. Is it universal for I2C that data transmission happens at the low level of the clock, or it's for the PIC I2C communication protocol? Okay, so generally, what we spoke about was I2C. We didn't speak literally to our own microcontroller. So we spoke about I2C generally. So 99% of the times, if you're not changing the features of the protocol, if you're using it as it is, actually I2C is a level triggered protocol and SPI is a edge triggered protocol. But if you want, you can make some changes according to your requirements to the protocol which is already available. So if you follow the procedure of the I2C communication protocol as it is in fact a level triggered protocol, and we will continue to use the same. Okay. All right. So let me open the driver code of this. So I'm going to open the project directly. So to open the project, let me first close this driver code of UART and open a new project. So we already have a driver code of the I2C communication protocol. I'm going to open that. Okay. So under I2C sources, here I have DS1307. So I'm going to open this project. So DS1307 is the name of the RTC. So it's the chip name of the RTC, DS1307. So I have open project, and in this template, what we are going to do is, the microcontroller being the master will actually read the time from the RTC. So it doesn't just read the number of seconds. It is going to read the number of seconds. It reads the number of minutes. It reads the number of hours as well. And once the microcontroller being the master is done reading the data from the RTC, that data should be displayed on the CLCD. So whatever current time you see, that will be displayed on the CLCD. So that is what we are going to do here. So me being the master, the PIC16F877A microcontroller should go to the slave, read number of minutes, read number of seconds, read number of hours, and whatever is read should be displayed on the CLCD. Okay, so let us implement this. And while the data is being displayed on the CLCD, I will display something like this: 2 digits of hour, colon, 2 digits of minutes, colon, 2 digits of seconds. Okay, so this is what I'm going to display on the CLCD. Now let us go with the execution of the program. Let us understand what has been written in the code. To start with, I'm going with the main.c. Okay, so first I have to do the initialization of the I2C block of our own microcontroller. So I'm calling the function called init I2C. Now, whenever you are using any communication protocol, so let's say it's UART, it is SPI, it is I2C, it is CAN, what is one thing you always have to maintain? Any of a communication protocol you take, what is one thing which you always have to maintain? Yes, the baud rate. So both the transmitter and the receiver should agree upon working the same baud rate. Now the baud rate of DS1307, that is the RTC, is in fact 100K. Okay, so it is I would say 100K, so means 100,000. Okay, or I can say 1 lakh, so whichever you are comfortable with. So that is the baud rate of the RTC. So I cannot change the baud rate of the RTC. So RTC is a simple chip which works with a fixed baud rate. So I can make adjustments with respect to the I2C block of my microcontroller. So I have to first initialize the I2C block of my microcontroller, and I have to set the baud rate to be 1 lakh. Okay. Now, I have to do the initialization of the I2C block, which is available on my microcontroller. So our PIC16F877A microcontroller supports I2C communication protocol. I want to initialize, I want to do configurations with respect to the I2C block of our microcontroller. So what should I be referring to achieve that? What should I be referring? Yes, we have to refer the data sheet. So I'm opening the data sheet of the PIC16F877A microcontroller. Now here is the data sheet. So as you know, it's a huge technical document. I cannot go in search of a particular thing that way. So I'm taking you to the table of contents. Can you look at this and tell me which section should I be referring to know about the I2C communication protocol? So which do you think is closely related to the I2C communication protocol? Okay. How is our microcontroller treated as? In this communication protocol, how is our microcontroller treated as? Come on. It's treated as a master. And what type of communication protocol is I2C? It's a synchronous. So now think and answer which section should I refer? Yes. So it's section number 9. Okay. So it's master synchronous serial port module. And this in fact has so many things to be discussing about. So let me focus. When you are configuring your microcontroller as a master, so you can either use SPI communication protocol, you can use I2C communication protocol also. Okay. For synchronous, for asynchronous, no clock. So giving baud rate for synchronous, we have clock, which is common for the master and slave. Then clock has some frequency, right? Then Y baud rate for synchronous. See, clock. Okay, that's a right thing. What Syed is saying is, in case of asynchronous, because there will not be any clock pulse available. Okay, so giving baud rate is something which is required. Now in synchronous, we have a clock pulse. Data transmission happens in a synchronous manner. Why do we need baud rate is the question. Now tell me, if it is baud rate, okay, so what does the baud rate literally say? What do you mean by baud rate? So baud rate in fact is nothing but number of symbols being transmitted per second. Okay, it's the number of symbols being transmitted per second. And symbols can either be of a single bit or it can be of multiple bits if you are using any modulation technique. Okay, so at low level of the clock pulse, I can transmit 2 bits also if I use any modulation technique. If at the low level of the clock pulse, I can transmit 5 bits also using any of a modulation technique. Okay, so by the period of low level completes, okay, by the time low level reaches high level, I can have any number of bits being transmitted. So in that case, if I'm transmitting 2 bits, by it is level triggered, I'm going to continuously transmit the data. Throughout the level, I'll transmit the data. So throughout the level, I can either transmit 2 bits or I can transmit 4 bits or more than that also. Now, if your device is transmitting 2 bits and the other device is not capable of receiving 2 bits at the rising edge of the, at the high level of the clock pulse, then the communication will not happen on a proper manner. So whether the clock pulse is available or not, it is necessary that the two devices agree to work with the same baud rate. Did you get this? Sayed? Okay. All right. So as I said, when you're configuring your microcontroller as a master, you can either configure it as serial peripheral interface. You can use SPI communication protocol or I2C communication protocol. So in our programming part, we didn't have a chip which supports SPI on our board. So we didn't have the programming part for it. So we are looking at the I2C communication protocol. So that comes under section 9.4. So I'm directly jumping to the I2C communication protocol. Now see, the MSSP module in the I2C mode fully implements all master and slave functionalities and provides interrupt on the start and stop bits in the hardware to determine a free bus. Okay, so please understand. So MSSP module in the I2C. Some noise? Am I not properly audible? I don't have any disturbance around. I'm not sure. Someone's mic is on. No. It's off now? Okay, fine. All right. So I was talking about the I2C communication protocol. So it can be fully implemented either as a master or a slave. Okay, our microcontroller can either be configured as a master or it can be configured as a slave. Now, the MSSP module implements the standard mode specification as well as 7-bit and 10-bit addressing. Now, whenever the communication should happen, let's say I am the master, master has to communicate with the slave. So, generally, how do you point out to a specific slave? How do you point out to a specific slave? We transmit the unique address. Now, assume my microcontroller at some point of time will act as a slave if another microcontroller wants to communicate. So when my microcontroller is acting as a slave, it can either give the address in 7 bits, it can give the address in 10 bits as well. So this option is not available for all the slaves. So generally the addresses of the slaves will be 7 bits itself, but there are devices which gets the addresses in 10 bits also. So our microcontroller, if it is configured as a slave, as I'm saying, it can either get configured as a 7-bit address or it can get configured as 10-bit address, 7 or 10-bit. But as of now, are we configuring our microcontroller as a slave? Are we configuring it as a slave? No. Now, because it is acting as a master, I don't have to be worrying about the slave's unique address. Okay. So let us not concentrate on it more. Now, 2 pins are used for the data transfer. So one for the serial clock, the other one for the serial data. So for the clock pulse, which pin do you think is configured as a clock pulse? The RC3 pin of your microcontroller is used as a clock pulse. Okay, RC3 pin of your microcontroller is used to generate the clock pulse, and RC4 pin is used to generate as a data line. Okay, so here it is RC3 pin, and this one is RC4 pin. Okay, so this is RC3 pin, this is RC4 pin. So the clock line is available at RC3 pin of the microcontroller. The data line is available at RC4 pin of the microcontroller. So RC4 pin is acting as a data line for the I2C communication protocol, and RC3 pin is acting as a clock line for the I2C communication protocol. Okay, next. The MSSP module has 6 registers for I2C's operation. So there are 6 total number of registers to be used for the I2C communication protocol. Now, out of the 6 registers, the first 2 are control registers. Then we have a status register. Then we have a receive or transmit buffer register. Then we have a shift register, and also we have a address register. There are a total of 6 registers which are associated to the I2C's operation. So first two are the 2 control registers. Then we have one status register, a buffer register for the transmission and reception, a shift register again for the transmission and reception, and an address register. Now you can see here, this must have been SSP con 1. It's a typo mistake. So SSP con 1, SSP con 2 and SSP stat are the control and status registers in the I2C mode of operation. So first 2 are control registers, then one is a status register. The SSP con 1 and con 2 are readable and writable. The lower 6 bits of the SSP status register are read-only bits. Upper 2 bits of the status register are readable as well as writable. So these 2 registers, all 8 bits are readable as well as writable. In the status register, first lower 6 bits are read-only, upper 2 bits are readable as well as writable. Then SSPSR is the shift register, which is used to do the data shifting in and out. So if you remember, in case of your UART communication protocol, you had separate shift registers. For transmitting, you had transmit shift register, TSR. For receiving, you had separate shift register, that was RSR. But here, there is only one shift register which is used either for the purpose of transmitting or for the purpose of receiving. Because we don't have 2 separate data lines here. There is only one data line which is either used for the transmission or it is used for the reception. So only single shift register will be available, which can either be used to shift the transmitting data or shift the receiving data. Similarly, I have only one buffer register. Whenever I want to write the data to the other device, I should write my data to the buffer register. Then it goes to the shift register. Then data gets shifted bit by bit. Similarly, if I have to read from the shift register, data comes to the buffer register. I just have to read the buffer register. Okay, there is a single shift register, there is a single buffer register, and that is because of half duplexity. Then after that, SSP ADD register, it is going to hold the slave device address when the SSP is configured in slave mode. So if the device is configured in I2C slave mode, then it is going to have the unique address. Okay, but when the device is configured in master mode, so if the device is configured in the master mode, The lower 7 bits of the SSB address acts as a baud rate generated reloader value. Okay, so whenever you are configuring the microcontroller as a slave, SSP ADD is the register where you can find the unique address of that microcontroller. But if you are configuring it as a master, SSP ADD is the register which is going to act as a baud rate generator. Okay, then in receiving options, SSP-SR and SSP-buff together creates a double buffered receiver. When SSP-SR receives a complete byte, it is transferred to SSP-BUF and SSP-IF interrupt will be set. Okay, and during transmission, the SSP buff is not double buffered. A write to SSP buff will write to both SSP buff and SSP SR. Okay, so that is, let me make a note here. So whenever I have to transmit a data, okay, whatever data I have got to transmit, I first have to write the data to the SSP buffer register. From the SSB buffer register, data gets returned to the SSP SR register and data gets shifted bit by bit via the RC4 pin of the microcontroller because that's the data line. Similarly, when you have to receive the data, okay, when you have to receive the data, so first via the RC3 pin, data gets returned to the shift register, that is SSP SR. Then the same data gets returned to the buffer register SSP BUF. So you just have to read the SSP BUF to get the data. So that is how the reception happens in the I2C communication protocol. Understood this? Clear with this? Okay. So this you don't worry, like what it says is, okay. So here let me repeat. SSP SR and SSP BUF together creates a double buffered receiver. When SSP SR receives a complete byte, it is transferred to the buffer register. Like it is just telling double buffered register in the sense, like it is like two registers being joined together. So first SSP SR data gets returned to the shift register, and when complete byte of data gets received by the shift register, it directly transfers it to the buffer register. Okay, so it's like both of them are correlated to each other. But while transmitting the data, whatever you write is first into the buffer register. Okay, from the buffer register, a write to SSP buff will write to both SSP buff and SSP SR. So in fact, whenever you write to SSP buff, immediately the same data gets returned to the shift register also. So not after you complete writing. Whenever you are writing, whatever data you write to the buffer register, immediately the same data gets returned to the shift register also. But in case of receiving, first data gets returned to the shift register, then all the data gets returned to the buffer register. That's the difference. Got this? Okay. Now let us proceed with the programming part. So we have to start configuring the control registers and status register. Now let us configure these three registers because we are supposed to configure three registers only, nothing apart from that. So the other three registers are buffer register, shift register, and address register. Starting with, I have three registers to be configured initially. two control registers and one status register. I'm starting with the status register here. So it's a 8-bit register with upper 2 bits having readable as well as writable permission, and their default values are zeros, and the rest of the lower 6 bits are having only read permission, and you're only supposed to read, and they default have the value 0 return inside it. Now let us start from bit number 7, which represents SMP. Why not configuring the other 3 registers? These 3 registers are not meant for configuration. The buffer register you're using to read the data, to write the data. Shift registers you're using to shift the data. And the address register is to generate the baud rate. Okay. Now coming to the status register, the first bit is SMP, which stands for sleeve rate control bit. Okay. So it's the sleeve rate control bit. Okay. Now, actually, in this case, right now we are not controlling any of a sleeve rate, so we can actually ignore it. So, if you have to know what a sleeve rate, it is actually the maximum rate at which the amplification can be done. Okay. So, the maximum rate at which amplifier can actually respond for any of a abrupt change in the input. Okay, that is sleeve rate. So now don't worry about the sleeve rate as we are not controlling it. So by default it has the value 0. So I'm going to retain it as 0 itself. Then the next bit is CKE, which stands for SM bus select bit. Okay. Now what does the CKE is? In either the master or the slave mode, you can actually configure the data bus whatever you have as a system management bus also. So that is only when you are doing lightweight communication. So you can make the data line act as a system management bus also. But I don't want to do it. Okay. So I don't want to use it for system bus. I want to use it for a full-fledged communication between the two chips. So I want to disable it. By default, it already has the value 0. So I'm not going to make any changes to it. Understood? Okay. So moving ahead, the next 6 bits are read-only bits. Let us understand what are they actually meant to. So they are read-only bits. So you cannot write into that particular bit. Now, the very first bit is data/not of address bit. It's reserved in case of master mode. Now, if it is reserved in master mode, do you think I should worry about it? Because we are configuring our microcontroller as a master, not as a slave. So don't worry about the slave mode. So let us focus on only the master mode. It's a reserved bit. Then P represents the stop bit. So based on the P bit, you can read the bit and say whether the stop bit has been received or not. Okay. While receiving the data, if this P bit is set to 1, it indicates that the stop bit has been detected. And if it receives a value 0, it indicates that the stop bit has not been detected. Okay, so P is the bit to know whether the stop bit has been received or not. Then S for start bit. So S return with the value 1 represents whether the device has received the start bit. S representing the value 0 represents if the start bit is not received. So S with 1 represents the start bit has been detected. S with 0 represents start bit has not been detected. Okay. So apart from that, the next is read or not of bit. Okay. Now I don't want to read what happens in the slave mode because my concentration is to go for a master mode only. Now read or not of write bit is the one which tells whether the transmission is in progress or the transmission is not in progress. In fact, what do you think r/w is representing? Transmission in progress, transmission not progress means what do you think? Can you say it in easy words? SDA line, right? So it is giving me the status of the SDA line. What can be the status of a SDA line? Yes. So SDA line can either be busy or it can be idle. Okay. So busy if the communication is happening, idle if the communication is not happening. So reading this r slash not of W bit will tell whether the bus will be busy or it will be free. Okay. Now r slash not of W with the value 1 represents transmit is in progress. Transmit is in progress means what is the status of the bus? If the transmission is in progress, what is the status of the bus? It will be busy. And if the transmission is not in progress, what will be the status of the bus? It will be idle. And actually, you cannot decide depending on only r slash W. You also have to take care of this. ORing this bit with SEN, RSEN, PEN, RCEN and ACKEN will indicate if the MSSP module is in idle mode. Okay, so I cannot just use r slash W. Along with that, you have to OR these many bits. These are the bits of another register we will see. So let me just make this point noted because I am going to make use in my program later. So r slash W ORing with this. Let me have it written here. I'm sorry. Okay. So ORing this bit in the sense r slash not of W. R slash not of W. Okay. So ORing this bit with all of this indicates if the SSP is in idle mode. Now after you OR, if you get a 1, that means what does it represent? If you get a 1, transmit is in progress. Means transmit is in progress means again someone's mic is on. Guys, please, Vinita, please take care of your mic, guys. Okay. So ORing this bit, if I get a 1, then it is representing the transmission is in progress, means bus is busy. Okay, it is reversed. So in case of that example we took, so SDA line giving the value 1 represented the bus is idle. SDA return with the value 0 represented the bus has been busy. It may not be constant every time. So it is 1. If it is 1, bus is busy. If it is 0, bus is idle. So that is with respect to the microcontroller, the PIC16A 877A microcontroller. Why do we need to OR? That is what the data sheet says. So to make a decision whether the bus has been idle or free, I have to OR r slash not of W bit with all of this bit. Okay. Now proceeding ahead, apart from that, the next bit is UA. It's update address whenever your slave is acting in 10-bit mode. Okay, if your microcontroller is acting as a slave in 10-bit mode, you may have to focus on this UA update address. So let me not focus on that. Next, BF is buffer full status bit. Okay, so whether you want to know what is the status of the buffer, you have to know it with the help of BF. In the transmit mode, if it is 1, receive is complete and buffer is full. If it is 0, receive is not complete and buffer is empty. Okay, so depending on this, you have to take the next action. So if BF is 1, so it says as of now receive is complete and the buffer is full. So you cannot transmit. Similarly, if BF is 0, receive is not complete and buffer is empty. Now you can use the buffer to do the data transmission. Similarly, in the receive mode, if it is 1, I already have a data to be transmitted, so buffer is full. Now in the receive mode, if BF is 0, that means I don't have anything to be transmitted. So whatever I had is done transmitting. So buffer is empty. So to know the status of the buffer register, you can make use of BF bit. So that is the 6 bits of the SSP status register. Any doubts in this? I literally didn't have anything to write here into my program. So I just went through this SSP status register. The next we have is the control register. We have two control registers. I'll start in a bit. Like if you want, you can note this. If there is anything to be noted, you can take a note. Okay, done. Can we proceed? Okay, BF is like TXIF and R/W is like TRMT in UR comparatively right. BF need not be TXIF itself. It is like both RXIF and TXIF you can say. Okay. Uh, and R/W is like T TRMT. Was there something like dear? Okay, yeah. Uh, like I can say R/W. Yes, yeah, I can use it to say whether the line has been busy or not. But it is not just R/not of W. So you have to or it with few more bits. So it is a combined work of multiple bits. So you cannot just depend on R/not of W. Okay. Now let us proceed with the next. So the next we have is the next control register. So I'm going with SSP con 1, the first control register. Now coming to SSP con 1, this is again an 8-bit register where the all the 8 bits are having both readable and writable permission, and by default they are representing the value 0. To start with, first bit is WCOL, the write collision detection bit. So it's the bit which is used to know whether there is a collision being detected or not. Now, first of all, when do you think collision is going to happen? When is collision going to happen? Yes, when two masters, it is not overloading here. When two masters are trying to communicate at the same time, then that is a collision. Okay. So when two masters start to communicate at the same time, there is a collision happening. But here, I have a master, I have a slave. Do you think there are any chances of collision in our programming? Is there any chance of collision? So always there is a master and a slave communicating. So we don't have any chance of collision. But still, if you want to know whether the collision is happening, so WCOL, you can write 1 or you can read in fact. So WCOL, if you read it as 0, there is no collision being detected. Reading with 1, then there is a collision happening. So like as of now, there is no consequence of any collision, so I don't have to be worrying about this bit. Okay. Next one. I have SSPOB, the receive overflow indicator. So this is the bit which is going to say while you are receiving the data. So if you are trying to receive any data, so whether the overflow is happening, you are going to check. So I may have to transmit, I may have to receive sometimes. While I'm transmitting, it's a don't care bit. But while I'm receiving, looking at this bit, I can check if there is an overflow happening. So if there is a flooding of data being transmitted by the slave to your master. So that can be identified with the help of SSPOV. Then we have SSPEN, which is nothing but synchronous serial port enable bit. So whether you have to enable the SD and SCL lines for synchronous data transmission or keep it disabled. So what do you want? Should I enable it or keep it disabled? I have to enable it. So SSPEN should be returned with the value 1. So in the initializing of I2C, that's the first thing I'm going to do. SSPEN return with the value 1. Okay. Next, CKP. It's a SCK release control bit. So in the master mode, it's an unused bit. So I'm not going to make use of it. Okay. In the master mode, it's an unused bit. Then the last 3 bits, in fact 4 bits, SSP M3 to SSP M0, it is used to select the synchronous serial port mode select bit. Now, how am I going to configure my microcontroller? How am I going to configure my microcontroller? In the master mode. Now look at this and tell what should I write if I have to configure it in master mode. It's 1000. So SSP M3 should be returned with 1. The rest of the bits should be returned with 0. By default, the rest of the bits are always having 0 itself. So what should I write to the SSP M3 bit? I should have it returned with the value 1. So that is the next thing we have written, SSP M3 with the value 1. And apart from that, it also gives me a formula to calculate the baud rate. So SSP ADD, if you are configuring it as a master, is used to calculate the baud rate. So I'm going to copy this. So this is the formula to be used to generate the baud rate. So clock here represents the baud rate. Let me have it noted here. Okay. So clock here is representing the baud rate. So you can see here, we have tried rephrasing it. Okay. So clock here is representing the baud rate. Let me have it written here. So I have to derive what should be returned to the SSB ADD for a baud rate of 1 lakh. So this I can rephrase it as baud is equal to F oscillating frequency divided by SSB AD plus 1. Okay. So after this, I have to write SSP ADD's value. So I will take it here and I'll do F oscillating frequency divided by baud. Okay, so divided by baud. Then this multiplied by 4 goes down to divided by 4. Okay, it's like this. We'll go to here, divide by 4 only. Okay, and this whole thing minus 1 is the SSP ADD. SSP ADD is a register which is used to have the address if the microcontroller is configured as a slave. So it will store the unique address if the microcontroller is configured as a slave. But if it is configured as a master, SSP ADD is used to generate the baud rate. It's a baud rate generator. So for a baud rate of 1 lakh, SSP ADD is returned with the value, with certain value. According to that value, your microcontroller will be set to work with the baud rate of 1 lakh. Got it? Okay. So then SSPEN with the value 1. Okay. So SSBEN is represented with the value 1. Okay. So what is this SSPEN? We already wrote it. So that is the next control register, SSP con1. The next we have is one more control register, SSP con2. Okay. Now I will come to the SSP con2 register, the second control register. Now before I come to the SSP con2 register, I think we will first understand what needs to be done. Okay. So, to proceed ahead, okay, let me go with SSP con2 directly. It's again a 8-bit register. It's a 8-bit control register which has all readable and writable bits written with the value 0. Okay. So, here we will not learn all of these bits as of now. Let us just focus on what happens here. See, whenever I want to know if the bus has been idle or not, r/w bit should be returned with the value 1. Okay, that represents the bus is busy. r/w with 0 represents the bus is idle. But I have to OR it with these 5 bits. Now, where are these 5 bits present? It is available on SSP con2 register. You can see the lower 5 bits. Okay, so that is the lower 5 bits. So if you see here, I will write it here. Okay, here. Okay, so I'm saying yes, ORing is mandatory. So R slash not of W, logical OR with all of these 5 bits. Okay, so all of these 5 bits I have to do the logical OR. Okay, now if this gives me the value 1, then it represents the bus is busy, and if it gives the value 0, then it represents the bus is idle. Now, how to get these 5 bits from the SSP contour register? How to get only these 5 bits from the SSP contour register? Should I do directly R slash not of W or with SSP contour? Do you think I have to go like that? R slash not of W logical or with SSP contour. Do you think I should write it like this? Okay. Now if I write SSP contour directly like this, what happens? How many bits of SSP contour am I using? I'm using all 8 bits, but I want the lower 5 bits only. How to get the lower 5 bits? How to get this bit, this bit, this bit, and correct, and with 0. And with 0 gives me what? It gives me 0 directly. And with 1, and with just 1, I will get SEN bit only. The and is right. To get the bit as it is, yes, I have to AND with 0x1f. Okay, so let me write it something like this. Assume the SSP contour has, let me write it here. Assume the SSB contour has XXXX. I don't know what it is. I want the last 5 bits as it is. I don't want the first 3 bits. So my expected result is 000 x x x x x. This is what I'm expecting. So in order to get this output, I should be performing AND. Okay, AND with the first 3 bits I don't want to change. I'm going to AND it with 0. The rest of the bits I'm going to AND with 1 1 1 1. Okay, so 1 1 1 1 I'm going to AND. So after I AND, what will I end up getting? I'll get 000 x x x x. So I can say R slash not of W or with SSB contour and with 0x1f. So if this gives me the value 1, then it represents the bus has been busy. And if this gives me the value 0, it represents the bus as idle. Correct? So this represents the value 0. Then it is saying that the bus is idle. Do you agree with this point? Okay. Now what we do here is, whenever I have to either transmit or receive, I may have to know the status of the bus. I may have to know whether the bus is idle or bus is being busy. So whether I have to start transmission, whether I have to receive the data, I may have to again and again check if the bus is idle or not. So I may have to repeat this logic every time. Before I start transmitting, before I receive, every time I have to check the status of the bus. Now that I'm going to have it return in a small function. So the name of the function is I2C, wait for idle. In fact, this function waits till the bus gets idle. Okay, this function is going to wait till the bus gets idle. So bus gets idle means what will be the value of this? So if the bus gets idle, what will be the value of this? It will be 0. So I have written it inside a while loop. until this falls down to 0, I will be stuck inside that while loop itself. The moment it falls down to 0, you come out of the while loop. So I am waiting till the bus is getting idle. So whenever I want to do the transmission or reception, I'm going to wait till the bus gets idle and I'm going to continue the communication. To wait till bus gets idle, whatever OR we did should give me the value 0. So I'm waiting till that value gives 0. The moment it gives 0, you come out of the while loop. If SSP con gives 11001, when AND with 0x1, it means some bits are not set and it's busy. No, the complete logical OR you are doing. So this is a non-zero value. It can be a 0, it can be a non-zero value. So if it is 0, then r slash not of w is also 0. 0 or with 0 gives 0. The bus has been idle. Okay, if either r slash not of w is 1 or this 5 which has any of a non-zero value, then logical OR represents 1 and the bus is being busy. Okay, so every time I want to check if the bus is being idle, I'm going to call I2C wait for idle function and wait till the bus gets idle. Understood? Okay. Now you have to first know what does these 5 bits represent. Let me go for the LSB side. The very first bit is start condition enable bit. So in the master mode, whenever you have to transmit a start bit, SEN has to be returned with the value 1. Okay, in the master mode, whenever you want to transmit a start bit, SEN should be returned with the value 1. Okay, so doesn't matter at what time you want to transmit a start bit. So you are supposed to write SEN with the value 1. So for that also, I have a function return. Okay, so for that also I have a function return. Whenever I want to transmit a start bit, I'm going to write a function called I2C start. Now what I have to do is just write SEN with the value 1. But before I write SEN with the value 1, I'm going to wait till the bus gets idle. So I'm calling a function I2C wait for idle. I first make sure the bus has been idle and then I write SEN with the value 1. So if I write SEN with the value 1 in the master mode, that is to initiate the start condition on the SDA line. Okay. Next, I have something called as RSEN, which represents repeat start. Okay. I also have something called as the repeat start. You want to do the repeat start. Now, if RSEN return with the value 1 is going to initiate the repeat start. RSEN with the value 0 initiates repeat start is in the idle condition. Now, assume you have done transmitting the data. You are done receiving the data. You want to still continue. Okay. So, you want to still continue. Now, if you want to still continue, the RSEN should be returned with the value 1. You don't want to stop. You want to still continue. RSEN is returned with the value 1. So for repeat start, I have another function return called I2C repeat start. Now what you have to do is, you have to wait till bus gets idle and you have to write RSEN with the value 1. Okay, Syed is asking SEN with 1 and S is equal to 1 need to keep to send start bit, right? So SEN is equal to 1 is to transmit a start bit. S is equal to 1 is to check if I have received any start bit. Okay. Next, whenever I want to transmit a stop bit, PEN has to be returned with the value 1. So PN with 1 initiates the stop condition. PN with the value 0 is stop condition idle. So whenever I want to transmit a stop condition, I'm going to call a function I2C stop. I'm first checking wait for idle, and then I'm having PEN return with the value 1. SEN automatically falls to 0 after sending a start bit. Yes, so any of a bit, once the start is done or once the stop is done, so they go to the default value. Okay, so understood stop, start and repeat start. So for every of the functionality, I have a separate function return. Okay, I want to stop, I want to start, I want to repeat. For every of the functionality, I have a separate function return. And in those functions, I'm writing the value to the bits of the control register. So Pn with 1 initiates the stop condition. RSEN with 1 initiates the repeat start condition. SEN with 1 initiates the start condition. Now, whenever I want to transmit a start bit, I'm going to have a function called I2C start. Whenever I have to do repeat start, I call a function I2C repeat start. Whenever I have to transmit a stop bit, I call a function called I2C stop. So the corresponding bits get updated. To repeat ORing logic, what we do, please pardon, my network was lost. To repeat ORing logic, see, to know whether the bus is idle or not, I have to OR r/not of W bit with the 5 bits of the SSP con2 register. So once it falls down to 0, the bus is in the idle state. Once it falls down to, it is still 1, the bus is in the busy state. In the I2C wait for idle function, I'm waiting till this r/not of W and this bit to have the, I'm waiting till it falls down to 0. The moment this falls down to 0, I come out of the function indicating that now the bus has got idle, that you can use it for the communication. So it's like I'm waiting till the bus gets idle. Okay, can you repeat why we need RSEN again? RSEN represents repeat start. So once you're done communicating with a particular slave, you don't want to stop, you want to continue the communication, you have to give a repeat start. So that is RSEN. And in some of the microcontrollers, they may not have the option of repeat start. In that case, you may have to stop and start the communication again. So that is why if you can see, I have it written in the comments also. I should stop and start the communication again. Okay. Fine. So these were the functions. If you want, you can make them a note. Okay. Are we using RSCN in our program? Yes, we will be using, because here our intention is not just to read number of seconds. So once microcontroller is done reading number of seconds, it may have to read number of minutes. It may have to read number of hours also. So I want to do the communication on a repeated manner. So I may need RSCN bit here. Ma'am, if we miss to initialize to R/W any bit of the register, in I2C or UART node gives particular warning or how debugging happens. So if you missed to write any of an initialization, it considers the default value of those registers and behaves accordingly. So it doesn't give you any warning. So all of the bits have their own default values. Now according to the default values, it behaves. Now, if you want to change the default settings, that is when you have to look at the configuration and do the changes by yourself. Else it behaves according to the default values initialization. Okay. Can we proceed? Next. All right. So going ahead. I have RCEN bit. Error or warning is not there if common not happen. If communication doesn't happen, no. So it doesn't give you any error or warning. Okay. Next, RCEN is receive enable bit. So whenever you have to receive the data, you have to enable that bit. So RCEN should be returned with the value 1 when you have to receive the data. Then ACKEN return with the value 1 is acknowledgement sequence enable bit. Okay. So it initiates the acknowledgement sequence on SDA and SCL line and transmits DT data automatically cleared by the hardware. See, ACKEN is to tell whether the master should transmit the acknowledgement or not. Okay. So ACKEN is a bit to tell whether the master has to transmit the acknowledgement or not, because it's an option. Master need not give the acknowledgement every time. Once it is done receiving the data or once it is done giving the data, it doesn't have to give the acknowledgement all the time. But it is up to the user's choice. If ACKEN is written with the value 1, master gives the acknowledgement. And if ACKEN is written with the value 0, master will not give the acknowledgement. Now, how is an acknowledgement given is with the help of ACKDT. Okay. If ACKDT is written with the value 1, it is like you have still not acknowledged. Okay. And if ACKDT is written with the value 0, it is acknowledged. Okay. Now to transmit whether the like acknowledgement is given or not given, you should tell whether to give the acknowledgement or not. So these two bits work together. Okay. Only if ACKEN is written with the value 1, acknowledged and not acknowledged will be passed. If ACKEN is written with the value 0, acknowledged and not acknowledged, it will not be passed. So these two work together. Then ACK stat is nothing but knowing the acknowledgement of the status bit. Okay, so it is the status bit. So you have to see, you have to check whether the receiver has given the acknowledgement or not when you are transmitting. Now, if ACK stat is returned with the value 1, acknowledgement is not received from the slave. ACK stat is returned with the value 0, acknowledgement is received from the slave. Then GCEN is general call enable bit, that is for slave mode only. So we are configuring it in the master mode, so we don't have to be worrying about it. And these are the three registers, the control and the status registers associated to the I2C block of the PIC16F 877A microcontroller. Okay, so this I'll show the acknowledgement bits with a few more in our case. Let me repeat again. These three bits only I will repeat. Okay, I think you are confused with only these three bits. Now, first is ACK stat. Okay, now what is ACK status? This is useful only when the master is in the transmit mode. Now, when master is done transmitting the data, don't you think slave should respond back after receiving the data? So yes, slave has to respond back. Now, this bit is representing whether the slave has given the acknowledgement or not. If ACK status return with the value 1, slave has not given the acknowledgement. So acknowledgement was not received from the slave. If ACK status return with the value 0, acknowledgement was received from the slave. Clear with ACK stat? Okay. Now coming to this, when master is transmitting, okay, so master has to know the acknowledgement from the slave. Similarly, when master is receiving, okay, when master is receiving, it is an option for the master to give the acknowledgement, right? You can see here, master transmits the second register's address. RTC gives the number of seconds from the register. Now, once the master receives the data from the slave, it is a choice of the master to give the acknowledgement. Now, you have to decide whether you give the acknowledgement or not. Now, to make that decision, you are going to make use of ACKEN. Okay. Now, if ACK master gives the acknowledgement to the slave, yes, master should give the acknowledgement to the slave after it is done receiving the data. So telling the slave that thank you, I have received your data properly. Okay, and that is not always required. So some masters may say, some masters may be arrogant and they may say, me being the master, why should I give an acknowledgement? That is still there. So if ACK is returned with the value 1, then master is telling, I will give the acknowledgement after I am done receiving the data. And if ACK is returned with the value 0, it is to tell that I will not give any acknowledgement after receiving the data. Okay. So ACKN is to tell whether I will give the acknowledgement for the data I receive. Now, how to give that acknowledgement is ACK DT. If I write it with 1, then your receiver, your slave will see it as acknowledgement is not done. If I write ACK DT with the value 0, your slave will see that the acknowledgement is done by the master. Okay. So this is to tell whether I will give the acknowledgement or not. And this is the one which represents the status of the acknowledgement. So when I say I will give the acknowledgement, the ACK DT bit will be transmitted to the slave. Now, if the slave receives 1 via the ACK DT, slave will understand the acknowledgement is not yet given by the master. ACK DT return with the value 0, slave receives it and understands master gave me an acknowledgement. Okay. Yesterday you told master gives 1 if the acknowledgement. So that, see, whoever is transmitting will pull the line up, whoever is receiving will pull the line low. So to give an acknowledgement. Altogether, it is taken care with a single bit here. ACKN to initiate the acknowledgement, and ACKDT equal to 0 means acknowledgement done by the master side. Correct. Understood? No need to check ACKDT if ACKN is disabled, right? Yes. So if ACKEN is disabled, this ACKDT value you don't have to update, and that will not be given to the slave, so you don't have to worry about it. ACKEN should be on for send the acknowledgement from the master. Yes, ACKEN should be one to send the acknowledgement to the slave from the master. So ACKDT, it is not read-only bit. It is you who will give the acknowledgement. It's the master. So if you are not done receiving the data, why will you give the acknowledgement? Only when you are done receiving the data, you give the acknowledgement. So to give the acknowledgement, you have to write ACKDT with the value 0. Okay. Understood this? And in fact, we are so much used to say 1 as success and 0 as failure, right? So we are very commonly used to judge 1 as a success and 0 as a failure. But here it is reversed. 0 return to ACKDT represents not acknowledged, and 0 return to ACKDT represents acknowledged, and 1 return to ACKDT represents not acknowledged. Okay, so generally we don't transmit ACKDT as it is, we transmit not of ACKDT. Clear? Okay. Any doubts with the 3 registers? Okay. Now let us see how to write the data. So what happens when your microcontroller should write the data to the RTC? So for that we have a function called I2C write. Whenever you have to write either to a slave or to a master, doesn't matter. Whether a slave has to write to the master or master has to write to the slave, they call I2C write function by giving the data to be returned. So the very simple way is I'm going to wait till the bus gets idle, and whatever data I have got to write, I'm going to write it into the buffer register. That is what we noted here. Whatever data I have to write, I have it returned to the buffer register. From the buffer register, data gets returned to the shift register, and bit by bit data gets transmitted from RC4 pin of your microcontroller. So that is I2C write function. So I'm going to wait till the bus gets idle, and I will have the data return to the buffer register. Now once I'm done writing the data, I'm going to return ACK status, not of ACK status. Okay, so ACK status when master is transmitting. Okay, so I have to know whether the slave is giving the acknowledgement or not. So if slave gives the acknowledgement, then ACK stat will have 0. If slave doesn't give the acknowledgement, ACK stat will have 1. So here it is reversed. So I am trying to return not of ACK stat from the function, so that 1 is indicated as success and 0 is indicated as failure. Okay, so once I'm done writing the data, I also give the status whether the receiver has given the acknowledgement or not. So that is I2C write. Understood I2C write? It's a very simple function. Whenever you want to write, so whether it is whether it is by the master or the slave, you're calling I2C write function. Doesn't wait for bus cause polling. Actually, yes, you are keeping constant I, but you have to wait. We don't have an other choice. We have to wait till the bus gets idle. Saurabh, why means what if we return as it is? You can return as it is, but interpretation will be quite different. So, like suddenly, if you see zero and you are saying it is a success, you might think, how come zero is treated as a success? So that is the very coding logic we have been using so far. So just to not see it that way, we are doing not of ACK start. But if you want, you can return ACK start itself. Accordingly, you have to take the action. Yeah. Now, instead polling, don't we have interrupt flag similar to URTXIF? No, we don't have an interrupt flag which says whether the bus is free or idle. Where we are getting ACK start, the slave will give. So whenever you are calling the I2C write function, you can collect that value and make a decision. So if I need anything for the decision, on a safer side, I'm returning it to the place where the write function is called. Okay. So we are still discussing about the functions. We are not implementing this yet. So we are still discussing about the functions which we require to achieve this. Okay. Whenever I want to transmit a start bit, here I have a start bit to be transmitted. I call I2C start function. I want to transmit a stop bit. I call I2C stop function. I want to transmit the unique address here. I call I2C write function. I want to read the value whatever RTC is giving. I call I2C read function. So we are just learning about the functions whichever are required to achieve this. Okay, so we are done with write function. The next is read function. So how to read from a particular I2C block. Whenever you want to read from the I2C block, you are going to call I2C read function. And here the function returns the data whatever is being read. Also, an option is given to the user whether you want the acknowledgement or not. Now, while calling the I2C read function, if 0 is passed, okay, so if 0 is passed, you can see here ACKDT return with the value 0. Let me write here. So ACKDT return with the value 0 is acknowledge. Let me comment it here. ACKDT return with the value 0 is acknowledge, and this one is not acknowledge. Okay. Now, if the user wants the acknowledgement, he is going to pass I2C read function with the value 0. Now, if user passes 0 as an argument, the user, that is the slave, needs acknowledgement. So actually it should have been the choice of a master whether to give the acknowledgement or not. But here we are giving the option to the slave. So master is asking the slave, do you want the acknowledgement? Or whoever is reading, it is asking, do you want the acknowledgement? Depending on that, whoever is transmitting, so will collect the acknowledgement. For example, slave is transmitting, master is reading. So master will call I2C read to read. So while reading, master will tell whether I will give the acknowledgement or not. Are you able to follow this? So acknowledgement to be given is always given as an option. It is not compulsory. So first I have to wait till the bus gets idle, and RCEN is returned with the value 1 to make continuous reception. Whenever you want to receive the data, RCEN has to be returned with the value 1. I'm going to wait till bus gets idle, and whatever is in the buffer register, that will be collected to a variable called data. Now, depending on the acknowledgement, so that acknowledgement bit will be updated. If ACK is 1, ACK DT is written with the 1, and else ACK DT is written with the value 0, and ACK EN is written with the value 1. Okay. So after that, I'm going to return the data back. I2C read function returns the data back. In our project, only after unique address sending the acknowledgement is mandatory, there ACK DT is equal to 0 is a must. Yes, only there it is a mandatory, but as a good practice, we generally will accept the acknowledgement most of the times to confirm that whether the master has received the data properly or not. So we give the acknowledgement. Master gives the acknowledgement in fact. Okay. So these are the functions we are going to make use of to implement these procedures in tomorrow's class. ACKEN is equal to 1 should be written first, then ACKDT. Doesn't matter. Once actually ACKDT should be written 1. Only then ACKEN should be first, sorry, first ACKDT should be written, whether you write the acknowledgement or not. Then when you say ACKEN with 1, that acknowledged data is going to get transmitted. So what we have written right now is correct. Even if we send acknowledgement, does RTC process it? Actually, in this case, it doesn't, but it's a good practice. So you do your task. It doesn't depend whether they are accepting it or not. It's like a function. So function may return the value, and it is not compulsory the returned value to be collected or taken care of. You can ignore that also. So it's completely up to the receivers, like whoever is transmitting. So tomorrow we will follow this procedure. All of the built-in functions are ready. We just have to follow this procedure. That we will do it in tomorrow's class. And we are still left with the initialization of the RTC. There is only one thing you have to do in the initialization of the RTC. We will do it in the tomorrow's class. Okay. All right, I'm going to stop here. So tomorrow we will complete the coding part, and if possible, we will go with the last communication protocol, which is CAN. So please have your attendance marked before quitting. Okay, here is the QR. Please have it marked. We'll continue tomorrow. Thank you all.